Okay, our next unit we're talking about rational functions and radical functions. So today I wanted to do a introductory lesson on rational functions. Watching this video will get you started for class tomorrow and also give you a basic understanding of what I'm looking for. So rational functions. What's a rational function? Well, a rational function is basically taking what we've learned so far this year, a polynomial, so let's say x squared minus 1 over another polynomial, x squared, plus 2x minus 3. Now again, this could be any polynomial over a polynomial. Just to give you a few more examples, I could have done x minus 1 over x plus 2. I could have done x cubed over x minus 3, and so on. But basically taking anything we learned from chapter 7 and applying it. What am I going to ask you to do right off the bat for a rational function? Well, let's go over the basics of what we've been doing. One thing that we are going to be doing, and it's not going to go away, is finding x-intercepts, finding y-intercepts, and last but not least, we're going to look at the domain of a rational function, and we're going to start to begin to call these discontinuities. As you may wonder why we call it discontinuities, if you were to graph y equals x squared minus 1 over x squared plus 2x minus 3, you'll see some different things start to happen. In these discontinuities, we have two different ways to refer to them. One is a removable discontinuity, and the other one is a non-removable. The non-removable discontinuity is what we're going to refer to as a vertical asymptote. Alright, so we're going to decide in the next slide what would be a removable discontinuity and a non-removable discontinuity. We'll also touch on x-intercepts and y-intercepts. So, as we move forward, f of x equals x squared minus 1 over x squared plus 2x minus 3. First off, let's talk about the domain. How do we find the domain? Back in chapter 2, we took anything that would make the denominator equal to 0, and we would say x squared minus 2x minus 3 cannot equal 0. X squared plus 2x. So we would factor x plus 3, x minus 1 equals 0. You could also FOIL this back out just to double check that it equals the above. And when it doesn't equal 0, so we would get x cannot equal negative 3 or 1. So as I transfer this to interval notation, negative infinity to negative 3 union negative 3 to 1 union 1 to infinity. As you take a second look at this function, you may have guessed that the top is definitely factorable as well. And how does that play a part in what we're going to be doing? So this is the next big part of introducing new topics for rational functions and the idea of vertical asymptotes and the whole concept of continuities and discontinuities. If I were to factor that rational, on top I would have x plus 1, x minus 1. On the bottom I would have what we just worked on, x plus 3, x minus 1. Now, applying our rules of exponents from the prior units, we can see that this quantity here will cancel with the quantity of x minus 1. They cancel each other out. Well, what does that mean? Well, it doesn't get rid of the fact that it can't equal 1 in the denominator, but this is what we call x equal to 1 is what we call a removable discontinuity. Sometimes this is called a hole in the graph. If you were to graph this function, you would see at x equal to 1 that it would look like a smooth curve. You wouldn't see any sort of funny business going on as you would see at x equal to negative 3. However, if you go into your graph and you then go look at the table, you'll see that x equal to 1 is undefined, as well as x equal to negative 3. Now, let's go take a look at this x plus 3. X plus 3 had no factors that were common on top, and it could not have been removed. Therefore, this is a non-removable discontinuity, and we call it a vertical asymptote. What I'd like you to do is graph that in your calculator and take a look at what x plus 3 on the bottom, where it's not removed. So at the value x equal to 3, or negative 3, what does the graph look like? And that x equal to 1, what does it look like? And compare the two. Continuing on, let's take a look at this. Now go back before we canceled out the removable, so that was removed. We have our domain that we looked at. So now once we remove it, we are left with f of x equals x plus 1 over x plus 3. Now let's take a look and find the y-intercept and the x-intercept. The y-intercept is when x equals 0. Well, if I go up to here and do that, I would get 1/3. 1/3, I would write that as a coordinate, and please make that a habit at this point if you're not already. So this would be a point on the graph, 0, 1/3. The x-intercept is when y equals 0. So if I go and set y equal to 0, I would have x plus 1 over x plus 3. So to find x-intercepts, I always tell students, once we get real used to this, to find x-intercepts, we want to take our numerator and set it equal to 0. This makes sense because 0 on top, 0 over any number will be 0. However, if we took the bottom and set it equal to 0, that would be undefined, and that's where vertical asymptotes come from. So this is the remaining piece. Take the top, set it equal to 0, and you get x equals negative 1. So in this case, we have one x-intercept, negative 1, 0. This point here, the x-intercept and the y-intercept could be graphed onto an xy plane, again, to give you a further idea as to what the graph of this looks like. So just to review what we've done, this is a rational function, x squared minus 1 over x squared plus 2x minus 3, a polynomial all over a polynomial. When we have this, some new things occur. Domain is always as usual, but in our domain we now have two different things. We have removable discontinuities versus non-removable, and both look different on the graph. So be ready to discuss that tomorrow in class. Secondly, we have the y-intercept as it's always been defined. Set x equal to 0. The x-intercept, set the numerator equal to 0. If you have any questions, please bring them to class to discuss. Thanks.